welcome to the fourth lecture of the course turbulence. So, in the last two lectures we discussed about the origin of turbulence and then how to find out the disturbance equation or disturbance evolution equation for instability analysis. Okay. So, we started with the Navier-Stokes equation and finally could find a disturbance equation in the last class. Okay. So, let me write this equation, and this particular disturbance equation is known as Orr-Sommerfeld equation. Okay. So, Orr-Sommerfeld Okay. So, this is what is our Orr-Sommerfeld equation, which we could derive in the last class, and the boundary condition for duct flows we considered that V hat at the wall of the duct from the center line, which is at h distance away. Okay. And this particular condition is coming from the continuity equation, okay, because the continuity equation gives us the I alpha c into u hat plus v hat prime is equal to 0. So, from the condition that u hat is also 0 at the boundaries. So, from that we can find that the v hat prime is also 0. So, from that particular condition we get this particular condition, please do understand. And for boundary layer flows, at y is equal to 0 or at wall is equal to 0, as well as v hat or y is equal to 0 is equal to 0 and v hat at what y is equal to infinity and v hat prime at y is equal to infinity is equal to 0. Okay. So, and the for last one for free shear flows, for free shear flows, the condition at plus minus infinity, okay, as well as at v hat prime at y is equal to plus minus infinity is 0. Okay. So, this is what we could find in the last class, and it was also mentioned that this equation is a fourth order ordinary differential equation with homogeneous boundary conditions. Okay. So, ordinary differential homogeneous differential equation with homogeneous boundary condition or homogeneous ordinary differential equation with homogeneous boundary conditions gives us an eigenvalue problem. Okay. So, this equation can be solved as eigenvalue problem, and here there are 3 parameters. One is alpha, nu or is the Reynolds number, as we will see just now, that if we normalize this equation or non-dimensionalize this equation, then we will end up with getting the Reynolds number in place of nu, and another parameter is your C. So, there are 3 parameters in this equation. Okay. Before I proceed, let us start with the non-dimensionalization of this equation. Okay. If we do the non-dimensionalize or if we do carry out the non-dimensionalization of this equation, what we get. Okay. So, for that let us consider that V hat prime star, okay, which is the non-dimensional, or instead of that V hat prime star, let us call this is phi. Okay. Phi is equal to, let us consider V hat divided by free stream velocity u infinity, and your u star equals to, let us consider u divided by u infinity, okay, and alpha, which is the wave number alpha star we can write as alpha into some length scale delta. Okay. So, alpha is what? Alpha is equal to wave number. What is this? 2 pi by lambda. Lambda is wavelength. Wavelength is in terms of some length scale, right. So, that means 2 pi by lambda, 2 pi by some length scale. So, some length scale needs to be multiplied, so that this alpha becomes non-dimensional. Okay. So, that is why the alpha star, it is a non-dimensional quantity if we multiply alpha by some length scale delta. Okay. It can be, for example, boundary layer thickness, it can be the duct half height, it can be boundary layer displacement thickness as well. Okay. So, this is one scale, then we have C star phase velocity, okay, non-dimensional phase velocity. Let us consider that to be your C divided by the free stream velocity u infinity. Okay. And along with that, this equation also has y. So, x and y or x and y star, x star or y star can be written as y divided by this length scale delta. Okay. So, with these scales, if you non-dimensionalize this Orr-Sommerfeld equation, okay, we get. Okay. So, we will be able to write this equation as u star minus C star, okay, then phi double prime minus alpha star square phi. Okay. I am not going ahead with the details of this non-dimensionalization. With these scales, if you just plug the scales in this Orr-Sommerfeld equation, you should be able to get these equations. So, please do this exercise on your own. Okay. And here we will get phi u star double prime equals to, here we will get I divided by alpha star, okay, Re. So, Re is based on delta, okay, which is the Reynolds number. Okay. And here we are going to get phi minus twice alpha star phi double prime plus alpha star square, it should be alpha star 4, here it is going to be phi. Okay. So, this is what is our non-dimensional Orr-Sommerfeld equation, and what are the non-dimensional boundary condition? So, boundary condition is similarly for duct flows, your scale with Popper scale for duct flows, you can consider phi at plus minus 1 as well as phi prime at plus minus 1 if you consider your length scale as h or half height of the duct, this is going to be 0. Okay. And for boundary layer flows similarly, for BL flows, once again you can write phi at at y is equal to 0 and phi at phi prime at y is equal to 0 is 0 and phi at infinity, phi prime at infinity is equal to 0. Okay. This is for your boundary layer flows, and for free shear flows, for free shear flows, similarly we can write that phi plus minus infinity is equal to phi prime plus minus infinity. These values are 0. Okay. And what are the parameters here? There are 3 parameters, for example, C star, alpha star and RE. There are 3 parameters in this equation. All right. So, now before we proceed, let us do one thing. Let us get rid of this star. Okay. This star let us get rid of, with the understanding that the moment we will consider the non-dimensional equation, non-dimensional Orr-Sommerfeld equation, let us consider the moment R is there, the equation is non-dimensional. Okay. So, that means what we can do, instead of this, we can just get rid of these stars and just write this equation as, we can just get rid of this star and write this equation u minus c phi double prime minus alpha square phi minus phi u double prime equals to minus I divided by alpha RE, then phi minus twice alpha square phi double prime plus alpha to the power 4 phi. Okay. This is with the understanding, the moment RE is here, we have to understand one thing, these are all non-dimensional quantities. U is also non-dimensional, C is also non-dimensional with proper scales. Okay. So, if we specify the Reynolds number is based on this particular length scale and velocity scale, then automatically all the scales comes in picture. Okay. So, there is, with this convention we can consider this particular equation. The moment we write this equation in this fashion, when that RE is coming in this equation instead of nu above, then we immediately understand this equation is non-dimensional equation with this boundary conditions. Okay. All right. So, this is what is our non-dimensional equation, and here there are 3 parameters. So, as I have mentioned, okay, 3 parameters in this equation. One is RE, alpha and C. Okay. So, these are the parameters. Now, you see here in this particular equation, how we can get the solution of this equation. Let us say for a given alpha value and RE value, for a given alpha and RE value, we will try to find the solution such that this equation is satisfied. While doing so, we will see for given real value of alpha and RE, there will be some complex values of C for which we will be able to satisfy this equation. Okay. So, for a given real value and given RE, this equation can be satisfied for some values of C which can be in complex domain. Okay. So, this is one of the way to get these solutions. Okay. So, that means what? For a given value of alpha and RE, this equation is going to satisfy only for a particular set of C. Okay. Only for some particular values of C, this equation will be satisfied, and those are the eigenvalues of this equation, because just like your Ax, your eigenvalue problem, maybe you understand Ax is equal to lambda x, where A is a matrix here and lambda is the eigenvalue, x is the eigenvector, and this equation this equation will have a solution only for some particular value for a given matrix. This equation will have a solution only for a particular, only for some particular values of lambda. You must have solved some 3 by 3 matrix, okay, 3 by 3 eigenvalue problems, 3 by 3 matrix of eigenvalue problems of this nature, and you must have seen some eigenvalues of lambda 1, lambda 2, lambda 3, right. For some particular values of lambda, only this equation will be satisfied. Similarly, you see this particular equation, if we provide alpha as real, RE as real, this equation will have some solutions only for some particular set of C values, and that C is going to be complex as well, because this function we have considered to be a complex, if you remember from the normal mode expression. Okay. So, anyway, that means you see that this equation will be satisfied for some particular values of C, and those C's can be considered as eigenvalues. Similarly, we can do one more thing. We can consider C to be C, or this C can be written as omega by alpha. Okay. C can be written as omega by alpha, okay, because C is equal to what? C is equal to frequency into lambda, which is nothing but omega divided by lambda. So, from that you can write this whole expression in terms of then in that particular case your parameter will be omega, lambda and RE. Okay. So, in that particular case you can consider omega is real and RE is real, you try to solve or try to find the solutions for some set of alpha which will satisfy these equations. So, in that particular case your alpha will be in complex domain. So, these two particular approach is known as, one is temporal growth, another is spatial growth. Okay. So, let me just come to that particular idea. Okay. So, temporal growth. So, first let me give you the physical idea. Temporal growth means what? For example, we have a surface, okay, over which there is a flow which is going on, okay, and if you if you consider a wave over this, let us say a wave is something like this. Okay. This is at t is equal to 0. Okay. Similarly, let us say this wave is there within a flow. So, in this wave amplitude at each and every x location at t is equal to 0 is same. Okay. Wave amplitude is not changing with respect to distance in this particular case. Let us say this is your distance. Okay. So, another case let us consider just below it. After some time t, let us say t is equal to t1, okay. You are constantly looking at that wave at that location itself, what is happening. After some time, let me just plot this wave which was seen at t is equal to t 0, you will see that wave so this is at x, at all position it is x. So, you see if you see this amplitude, amplitude of this wave and amplitude of this particular wave, this amplitude smaller than this amplitude. So, at t is equal to 0, the amplitude at all this location, if it is a naught, then at t is equal to t 1, amplitude a 1, definitely a 1 is greater than a naught. That means, with respect to time, the amplitude is increasing at all these locations simultaneously. So, this is what is our temporal growth, means amplitude of the disturbance at any point in the flow is growing with respect to time. It does not matter whether it this location, at this location, at this location or at this location. So, this is what can be considered as temporal growth. If you consider at t is equal to t 2, this amplitude will be even bigger. Okay. So, that is what can be considered as temporal growth. Okay. So, let me show you, if this is at t is equal to t 3, if you consider the same thing, then this is going to be even larger. So, amplitude is going to grow like this. Okay. So, that means you see this is, let us say, amplitude is a 2 and this is at t is equal to t 2. Okay. So, you see the amplitude of this wave at t is equal to t naught is this, and as time progresses, what is happening? The amplitude of this particular wave is increasing with respect to time. So, this growth is happening with respect to what? Not space, because at all space it is same growth. With respect to time it is increasing at any position you consider. So, this is what is the temporal growth, which is increasing with time. Okay. So, now this is temporal growth. Now, consider your spatial growth. Okay. So, spatial growth consider once again the same set of condition, that is a flat surface and over which let us say there is a wave at a particular x location. Let us say this is at x is equal to x naught. So, at x is equal to x naught, one disturbance is starting and is seen to be like this. Okay. So, you see in this particular case amplitude, this is at t is equal to t naught. You have just taken a snapshot of the wave at t is equal to t naught over all this spatial distance, and you could see this particular wave, and from this it is clear, see the amplitude is increasing with respect to space. You see, as you are going downstream, your amplitude is also increasing with respect to space. That means, at some other time, if you consider, let us say this is at some other finite time t is equal to t 1, at t is equal to t 1, if this distance is x 1, so and this is once again is x naught. So, from this x naught to x 1, at whatever time you look, it does not matter. This amplitude at any location within this distance, this amplitude is same. Whatever this distance here, let us say whatever this distance is x naught here or x 1 here, this is always fixed. But if you go downstream, then you will see this is increasing. Okay. So, you see at any distance amplitude at a particular location is not growing with respect to time, because if I look at this particular position, for example, let me take a color chalk. Let us say at this particular location I would like to see the growth of a disturbance at this particular location, or at this particular location, for example, if I would like to take the growth, then this is the corresponding location here. So, at any time if you look at this growth, it is not changing with time, because at the same location you are looking with respect to time, it is not changing, whereas this is not the case in the previous case. At this particular location, if you see, it is changing with time, it is changing with time, but this is at this location, at any time you look at, it is not changing. Then it is changing with respect to what? It is changing with respect to space. So, this is what is our spatial growth. Okay. This is what is our spatial growth. As the disturbance is propagating in the downstream direction, its amplitude is increasing. Okay. So, this is what is the spatial growth. Okay. So, while solving this particular equation, there are two approaches. One approach is your temporal approach, another is spatial approach. Okay. In the temporal approach, we consider alpha to be real and C to be complex, and in spatial approach we consider omega, which is omega by alpha here. So, omega is real and alpha is complex. So, these are the two ways to solve this equation, spatial or temporal, and there is a relation also between spatial and temporal. I will not go into that details. Okay. Using the group velocity and phase velocity, group velocity, we can have a clear relation between these two approaches. I will not come to that details, because it is not that stability analysis course, rather it is just introduction to the stability part as a particular aspect of turbulent flow. So, anyway, so in temporal approach, so let me just write it here. Temporal approach temporal approach, what do we give? Alpha we provide, RE we provide, and we try to find out CR and CI. Here C is complex. Okay. That means, we are trying to solve this equation for a given value of alpha and RE. What are they? I mean, that when that solution, when any solution is going to be there, for that solution what is the value of CR and CI. Okay. So, this is the temporal approach. In temporal approach, this is what we do. Okay. In spatial approach, what we do? We provide omega, okay, RE, and we find out alpha R and alpha I. Okay. We try to find, given this value and this value, we try to find for what value of alpha R and alpha I this particular equation is going to be satisfied. Okay. So, those are our eigenvalues. Okay. All right. So, these are the two approaches, and here I just need to give you a little more description what is alpha I and CI. So, here that CI is the temporal growth rate okay, and alpha I spatial growth rate. Okay. Why? Let us see. So, if you can remember that we considered that V prime is equal to, prime means here the disturbance quantity, that V hat which was a function of y, exponential I alpha x cosine phi plus y sin phi minus c into t. So, this was our normal mode consideration, if you can remember from the last two classes, right. Then we saw a two dimensional disturbance for a two dimensional basic flow is more unstable or will give us the minimum critical Reynolds number. Okay. So, that is why a two dimensional disturbance or two dimensional base flow is more dangerous as compared to three dimensional disturbances. Therefore, we could get rid of this particular quantity. That means, in our normal mode approach, then we can write simply this as I alpha x minus C t, because phi is equal to 0 here, disturbance is propagating along the x direction, that is what we have talked about in the last class, right. So, that means this is what our normal mode expression, or if we consider the non-dimensional value of this equation or non-dimensional equivalent form of this equation, we can write simply phi is equal to our phi, the non-dimensional phi, or phi prime is equal to, you can consider phi of y exponential, these are all non-dimensional quantity, I alpha x minus C t. Please do understand this is the non-dimensional stuff, because consider that we have normalized everything. We have normalized everything here. Okay. So, that means you see this is means that phi, which is function of y exponential I alpha x minus C t. So, this phi here, please do understand, this particular phi is this phi. Okay. So, this phi is basically, this is the amplitude function. Okay. So, you see from this particular equation, let us see what we get if we consider the spatial approach. So, that means phi prime, which is the disturbance quantity here, please do understand it is not derivative with respect to y. Okay. So, that means you see that phi y, if you consider this alpha x minus alpha C t is nothing but your omega t. Okay. Alpha C t is nothing but your omega t. So, this equals, you see, phi of y, our spatial approach. Spatial approach, what I said, omega should be real, alpha should be complex. Okay. That means exponential I alpha r plus I alpha I, alpha is complex, means its real part is alpha r, its imaginary part is alpha I, into x minus omega t. So, if we simplify this, you see I we can take it inside, then what do we get? Phi of y, then you see exponential, the complex part will take it out. So, complex part is going to be I alpha r minus I omega t, this will be the complex part, and this I will be I square. So, I square is equal to minus 1. So, that means we can write this I alpha r x minus omega t, okay, and the other part is going to be exponential this I into this I. So, minus this is going to be minus alpha I x. Okay. So, this is what is our this disturbance quantity, non-dimensional disturbance quantity here. Okay. Now, you see what is this at a given y, at a given y and at given x, or at given y, what is going to happen? This one, it is just like e to the power I theta, means cosine theta plus I sin theta. So, this particular function, this is going to give you only a sinusoidal oscillation, and this part is real, this part is also complex. Okay. This is also a complex function, because phi of y is a complex function at a given y. Okay. So, essentially you see, if you if you define your amplitude, okay, if you define your amplitude as e power minus I alpha x, then you see, let me just transfer the quantity here. So, we wrote this equals to phi of y, which is also a complex function, exponential I alpha x, or sorry, alpha r omega t into exponential minus alpha I x, right. So, this is complex quantity, which is nothing but your sinusoidal oscillation. Okay. And if we define this as our, and so this is the real part. So, this can be the amplitude to the sinusoid. Okay. So, let us consider this to be amplitude. That means, if this is the amplitude, so let us define A is equal to x, then you see what we can write, dA dx is equal to your, sorry, not I, it is minus alpha I am sorry, okay, minus alpha I exponential alpha I x, or we can write this as, what is this quantity then? Our A only, right. So, 1 by A dA dx is equal to minus alpha I. So, you see here, what is this? One by A dA dx, A is the amplitude, A is the amplitude means what? We are talking about the spatial growth. So, spatial growth means the wave is increasing like that as you are increasing the distance. So, this is exponential, that is what it says. Okay. That means, this amplitude is increasing, okay, with increasing with what? Distance x. So, dA dx rate of increase divided by, let us say, the initial amplitude. What is that? That is nothing but your growth rate, because rate of amplification, that is what it minus alpha I. That is why the minus alpha I your spatial growth rate. Okay. So, hence minus alpha I is the spatial growth rate. Okay. In the similar fashion, it can be shown that for your temporal approach, it can be shown that your C I, okay. So, alpha C I which is nothing but your omega I, which will be the growth rate, okay, or equivalently C I is your basically growth rate, okay, temporal growth rate. Okay. So, that you take it as an example like this. If how to proceed, if phi prime phi of y exponential I alpha x minus C t. Okay. So, what you can consider this here u I alpha x minus alpha into C, which is nothing but your omega. Okay. So, in this particular case, temporal case we are talking about, means alpha should be real, omega should be complex. If you go ahead, you should be able to show that omega I, which is equal to alpha C I, is your temporal growth rate. Okay. Please check that. This will be your temporal growth rate. Okay. So, now it is clear that what is called temporal growth rate and what is called spatial growth rate. Okay. All right. Let us say with this we can solve the equations. So, before I proceed, I need to tell you what are the solution methods. I have forgotten to tell. So, anyway, let me just mention here. So, how this equation first of all can be solved, okay. That is what we would like to say. So, there are various methods to solve this equation. So, mainly there are three approaches which can be seen in the literature. That is what I am going to mention here. So, the first method, solution method, solution of the disturbance equation, okay. That is what we are talking. Solution method. So, there are three solution method. One is matrix method, with spectral or finite difference discretization. Okay. So, for this you can see the book by Schmidt and Henningsen. Okay. See this book, which I have already mentioned in the first course handout, I think. Then second method, shooting method, it is a boundary value problem. One of the solution method for boundary value problem is the shooting method. Okay. using orthogonalization. Third one, shooting method using compound matrix okay, which is known as CMM, okay, CMM, compound matrix method. Okay. So, details of these techniques is available in a book by title Instabilities of flows with and without heat transfer and chemical reaction. Chemical reaction. Okay. So, let me write it above, it is not coming, it is not visible. So, here chemical reaction by Professor T.K. Sengupta. Okay. So, Professor T.K. Sengupta was the faculty of the Department of Aerospace Engineering, but he is superannuated and presently he is at some other IIT. Okay. He is working. So, anyway, you please see this book for this particular method, okay, where he has given the detailed description of this method. Okay. So, these are the solution method of this particular equation. Okay. All right. So, if we solve this equation, what do we get? So, let us say we are able to, for a given velocity profile, we are able to solve this equation. If we solve this equation, for example, considering temporal spatial approach, what we will get? We will get a set of eigenvalues. Okay. So, from this set, if it is spatial approach, if minus alpha I, if minus alpha I is greater than 0, then you are going to get instability, because the amplitude in that case is going to grow with time, sorry, space. If you find that C I greater than 0, then you are going to get the flow to be temporarily unstable, right. So, let us say we have solved this for a particular given velocity profile and how we can interpret the results. Okay. So, let me just give you a brief overview of the same here. So, let us say we have solved that equation in temporal approach first. So, if you solve this equation in temporal approach, then in temporal approach let us say we have solved this equation in temporal approach and spatial approach. Okay. So, let us consider this particular equation we solve for a boundary layer flows. Okay. So, for a boundary layer flows, this will be our condition, and for a boundary layer flows the velocity profile is given. That means, your velocity profile is something like this for a boundary layer, right. So, this is your wall normal height, let us say non-dimensional value y, and this is your let us say non-dimensional velocity u. If it is non-dimensional velocity, if it is non-dimensional by using free stream velocity, so maximum this is going to be 1, right. So, for this given velocity and given Reynolds number, if we solve the equation for each alpha and for each given alpha and given RE, we will get a set of C values for which this equation will be satisfied. And we have to look what is the most unstable eigenvalues, okay. Means what is the maximum value of C I, okay, because C is maximum means what? Growth rate corresponding to that particular wave is maximum. So, we will be interested to that wave only which is growing fast. Okay. So, let us say we have solved that for different alpha, different RE and obtain those set of Ci, the maximum values of Ci. And how to reinterpret the data then? To interpret the data, let us consider this is our Reynolds number axis and this is our given alpha, given non-dimensional alpha, let us say. Okay. So, for we have a mesh, let us say invisible mesh. Using this invisible mesh, we have solved the equation for at different point, means we have considered fine enough mesh, and for each and every value of this mesh point we have solved the equation. That means, for each and every point of this equation we have one maximum Ci value which is the most unstable Ci we are considering. That means, in the each and every point of this in this plane you have a value of Ci which is the most unstable value. So, what we can do in this grid point, since you have various values of Ci, to interpret the result, what we can do? Because we know that if Ci value is less than 0, flow is stable. If Ci value is greater than 0, flow is unstable. So, using this Ci value, then what we can do? We can draw a contour plot. Okay. So, if we can draw a contour plot, that will demarcate between stability and instability. How? So, let us say we have done that job for a given velocity profile, and this is what is our kind of Ci is equal to, let us say this is what is our Ci is equal to 0 line contour. Inside Ci greater than 0, outside Ci less than 0 in this parameter space. Okay. So, that means you see there is a point or there is a value of Reynolds number, this value RECR, below which all the alpha and C or RE for all wave it is stable. Okay. If your Reynolds number is below this value, you are in the stable regime of the flow. If your flow Reynolds number is greater than this particular value, then you may be inside this domain, if you are within this range of alpha. Okay. So, that means what? That this if you are within this zone, then your wave is going to grow with respect to time, that is what it says. Okay. So, this is what is the minimum critical Reynolds number which can be found solving this equation for a given velocity profile for a given flow. Okay. I have just taken an example for the boundary layer, okay, with which I am most familiar with. Okay. So, anyway, now let us consider the spatial approach. So, in the spatial approach, what was the approach we talked about? We said Reynolds number is given quantity, omega is given quantity, and alpha r, alpha I, which are the eigenvalues, needs to be calculated. And we are interested on the most unstable eigenvalues for which minus alpha I is the maximum. That means, in the similar fashion, if this is our Re and this is our omega, which is non-dimensional, in this we have a mesh just like this. Okay. We have a mesh, this can be very fine enough, so that at each and every point you have a solution, and you can, so each and every point of this grid you have a solution for this equation, and you have the value for maximum value of minus alpha I. Then you put a contour here. Okay. To interpret the result, simply you plot it in terms of the contour value. Let us say this is what is your alpha I contour. Okay. So, this is what is your minimum critical Reynolds number for this approach. Okay. And within this, your minus alpha I is greater than 0, and outside your minus alpha I less than 0. Okay. And this is your alpha I is equal to 0. Okay. So, minus alpha I greater than 0 means alpha I should be negative. If alpha is negative, the wave will grow. If alpha I is positive, then the wave will decay. Okay. So, that is the case for a spatial wave. Okay. So, now interesting point, you see this for example, you consider in this particular case, okay, a particular wave. Let us say, let me just draw a picture here which will be helpful for you, I believe, before I proceed with that. So, for example, we are considering a boundary layer flow at this point, right. So, there is a boundary layer flow. Okay. The flow is going like this, right, and this is distance x. Okay. So, R is increasing, if it is based on the delta or bound displacement thickness, whatever may be the case, R is increasing means actually for a given velocity profile, for a given free stream velocity, you are actually increasing the distance in the downstream direction, because as you are going downstream, your delta is increasing, or displacement thickness will increase, or your x will increase, right, for a given velocity profile. Please do understand. Okay. So, let us say the critical Reynolds number, if we find it out for this particular case, for boundary layer case, based on the displacement thickness, it is found to be Re is equal to 520, okay, based on okay. That means, let us say this r is equal to 520 for a given velocity profile is coming at that particular location. Okay. At this particular location, that r is equal to 520 is first achieved. That means, if you excite a wave at this particular location with a particular frequency, till this wave reach at this location, it will decay, but after that this wave is going to grow with respect to space. Okay. That is what it says. That means, you see here omega. So, that can be very interestingly noticed, omega, which is what? It is a non-dimensional frequency. That means, omega is equal to 2 pi f, okay, which is f. So, this is omega is non-dimensional, f is what? 1 by t, t means, that means 1 by t. So, this is delta star divided by u. So, this is a non-dimensional quantity, because this is the u means u infinity here, please do understand. Okay. So, that means this is the non-dimensional quantity. So, you see what, how I can manipulate this stuff, 2 pi, let me take u infinity once again square here, okay. Take a nu here, another nu you can multiply above. Okay. So, this is just a manipulation. Now, I can consider this quantity as Reynolds number, keeping all other same. So, that means, this is f, this is f into nu, f into nu divided by u infinity square, which is also non-dimensional, right. This is meter square per second 1 by second. So, meter square per second square, meter square per second square. So, this is also non-dimensional. So, you see into this is R e. Here we are talking that R e, we have taken a scale of displacement thickness. So, that means omega is equal to, for a given frequency, it is a constant C into R e, y is equal to m x, x is R e, y is equal to w. So, this is a straight line which is passing through this point origin. So, any frequency, any constant frequency, this is the line. So, this frequency, let us say this is f 1 is this one. If you consider another frequency, let us say f 2, this is this 2. Okay. So, what it says, any constant frequency in this particular case, this is just a line. Okay. This is just a line. Let us say somewhere for this particular frequency, let us say here. So, here you are exciting f 1, a given frequency, let us say 50 hertz. So, this 50 hertz is not going to grow till it reaches this point. Okay. So, from this diagram, what do you say, that this particular wave is going to grow, going to decay till this. The moment it has reached that critical location, for this particular wave, it will start growing, okay, and this particular branch is called branch 1 and this particular one is known as branch 2. Okay. And you see, that means this wave is going to grow, a wave of frequency f 1 is going to grow from this point to this point. And what is that? So, a wave, if you come down, see this is R e, which is equivalent to x actually for a given velocity. R e is increasing, x is also increasing. That is the way you can increase R e for a given velocity and given your viscosity. Okay. So, that means if you plot it here, this one is going to be your, let us say, this is what is your minus alpha I. Okay. So, your minus alpha I, see below this point is going to be decaying, the minus alpha I value will be going towards 0, then from this point it will start increasing, then again it will be 0 at this location. Okay. Sorry, it should come this way. So, this is what, let us say, your this is actually your x, and this, let us say, this x is equal to 0 and your minus alpha I is equal to 0. That means, your minus alpha I is less than 0 before this particular point, before this particular x. After that, the moment the wave has reached to that x is equal to CR location for this particular wave, then it is going to grow. Okay. After that, again the growth will be less, and slowly it will become 0 and become negative. Okay. So, what is happening for this particular case? So, this is what is our minus alpha I for this particular wave. Similarly, you can have another minus alpha I for this particular case. Okay. And so on, and you can integrate this. So, based on this, a transition prediction model has been devised. Okay. That is what is called semi empirical transition model. We will discuss, I think, in the next class, because this will talk little later. Okay. Before I mean, at the end we will talk about, based on this particular stability theory, how a transition prediction model can be achieved. Okay. So, that I will talk later on. Okay. So, anyway, so this is the interpretation of the stability analysis for this given velocity profile in a boundary layer flow. One point needs to be mentioned here, these two branch 1 and branch 2, as you increase Reynolds number, they will slowly they will slowly come and merge at some downstream location. But if your velocity profile has a point of inflection, they are not going to do so. Okay. What is the case for free shear flows very often. Okay. So, anyway, these are little advanced thing. I think if someone of you are interested, can go through some of the text which has been already mentioned, okay, on this particular aspect. Okay. All right. Now, before I come to the transition prediction model based on this particular analogy, what I would like to introduce something what is known as implicit instability. When this particular equation was devised in 1907 and 8, people thought actually viscosity will play a stabilizing role. Viscosity will not help the disturbance to be unstable. Okay. So, therefore, what they consider? They only consider that to find out the stability, it is enough to consider the left hand side of this equation. Okay. So, there is no need, since I mean viscosity can be considered to be viscous part can be considered to be a stabilizing effect on the flow. So, you only talk about the implicit instability, that is considering the right side of this equation to be 0. Okay. And this equation is known as Rayleigh's equation. Okay. So, from this equation, before or I mean without solution itself, we can get some interesting results. What are those? See, what we can do from this equation, little bit manipulation. So, this is what is our implicit equation, right. So, we can write this equation as this. We have just divided by this quantity here. Now, let us do one thing. Sorry, this is needed. I am sorry. So, let us multiply by the complex conjugate of this phi value. If we do that, then we get what? Phi complex conjugate, let us say phi star, and phi double prime minus alpha square phi and phi star, which is nothing but this minus you are multiplying by phi and phi star. So, this is once again is going to be u double prime absolute value of phi u minus c is equal to 0. All right. So, now let us integrate this equation. Let us integrate this equation, let us say for one boundary to other boundary. If it is duct flow, then minus 1 to 1. If it is boundary layer flow, from 0 to infinity. If it is free shear flow, minus infinity to infinity. Just for the example, let us take minus infinity to infinity, and let me write another line. Let us integrate this equation, then what we get? Integrate the equation, integrating we get dy minus dy minus infinity to infinity dy u minus c is equal to 0. So, let us see, sorry, it should be star. So, if we integrate this particular part as integration by part, then what we can write? Phi star prime into phi star minus infinity to infinity. Then another part is going to be there, that is your minus infinity to infinity. This is the first function. So, phi star prime integral of this phi, this is phi star prime and this is phi prime, and this is your dy alpha square should be no alpha square is here. So, minus, and this is minus infinity to infinity, this one is going to be alpha square phi square dy minus infinity to infinity dy u minus c, okay, is equal to 0. Phi star prime so first function no, there is first function and integration of the second function phi prime, phi this, there is a mistake here. Okay. So, this is your first function into integration of the second function phi prime then, because it is a double derivative, and value of this quantity from minus infinity to infinity, which is going to be 0, because phi prime at both the ends is 0. So, this part is 0. So, we are left with this part, this 3 part. Okay. So, or we can write this whole equation as you see, minus infinity to infinity, this is going to be your phi prime square dy, okay, or this plus alpha square phi square dy, okay, is equal to, or yeah, minus, this is equal to minus alpha, sorry, minus infinity, and here u infinity minus you take c star, okay, you have to take, sorry u minus c star, u minus c star phi square dy, this can be written as u minus c square, because we would like to c is a complex here. So, that means, if we multiply both this side by u minus c star, then this will become your positive quantity. So, that means, if you see that u minus c r means, what we can do here, there will be two part of this integral, one is your basically real part, another is your complex part, okay. And one will be real part, one will be complex part. So, if we do that, we will see from the complex part, complex part is going to come as C I u double prime. So, complex part of this equation, let me do it here, okay. Or let me write this equation once again. So, minus infinity to infinity phi prime square plus alpha square phi dy, okay, and that is going to be your minus. So, this is minus u prime, sorry, u double prime u minus c r, okay, u minus c r, u minus c square minus infinity to infinity minus infinity to infinity dy, this sorry, that another part I am sorry, okay, another part let me write. So, this is going to be positive I C I, okay, positive I C I okay. So, now it will have two part, one is real, another is imaginary, right. So, if we separate out, let us see. So, real part, what is real part? Real part of this equation is going to be minus infinity to infinity, this is phi prime square plus alpha square phi square, sorry, that square is missed here. So, dy, okay, and this is going to be positive, let me write infinity, and this is u double prime C r minus u, okay, u minus c whole square d, sorry. So, this is going to be square dy, okay. So, this is your real part and imaginary part. Imaginary part, if you consider, what is going to be I C I, sorry, C I integral minus infinity to infinity u prime phi square u minus c whole square dy is equal to 0. So, these are the two part we have got. Okay. Some interesting results we have achieved. For example, you see this particular part. For C I non-zero, this integral to be 0, that u double prime has to change sign somewhere in the flow domain, otherwise that summation cannot come to 0, because this is positive, this is positive. So, u double prime has to change sign somewhere in the flow domain. That means, u double prime somewhere has to be 0 in the flow domain. That means, u double prime is equal to 0 means what? There should be a point of inflection in the velocity profile. Okay. So, there should be a point of inflection in the velocity profile. So, Rayleigh pointed out that it is necessary for instability that the velocity profile has a point of inflection. So, from this, the Rayleigh's theorem says so theorem 1 okay. Okay. It is necessary for instability that the velocity profile has a point of inflection. Okay. So, what it says, if the flow is unstable, if the flow is invisibly unstable, it says the velocity profile must have a point of inflection, but the converse is not true. Means if the flow is having a, or if the velocity profile is having a point of inflection, it does not guarantee that the flow is unstable. Okay. Because you see here, for C I, this particular expression or u double prime will have a, u double prime will be 0 somewhere in the flow domain for C not is equal to 0. So, C I can be less than 0, in that case it is stable flow. So, even for a stable flow, that profile can have point of inflection. So, therefore, if the flow is unstable, then it is necessary that the flow is having a point of inflection. Okay. The converse is not true. That means, if the flow is having a point of inflection, it does not guarantee the flow will be unstable. Okay. But if the flow is invisibly unstable, means the velocity profile will have a point of inflection. Okay. So, this is one of the theorem which is coming out from this particular. So, now today is time is over. So, I will come back to this in the next class, and we will have some more exciting results to describe, to discuss. So, that we will do in the next class. Okay. Let us stop here for this lecture. Thank you.